Howdy and welcome back. So we will begin today's lesson with a brief review of binary search trees. If this isn't sufficient, if we're going through this and it seems like there's some pieces missing, I'll strongly encourage you to go ahead and review the binary search tree lessons. The reason being is that we're going to have a very kind of condensed and quick review here, as I expect that you're already familiar with this material. So binary search trees, we said this was a tree who was composed of nodes, and at each node we could step either to the left or the right. So there was a binary number of children. There was either one children, two children, or no children's for each node. We said that a binary search tree put a sort of ordering of such of the nodes that are comprising the tree. So it's going to be an organized binary tree, and it is going to be represented using, again, this linked data structure in the sense that the nodes are going to be connected together through pointers to the either their parent, the node that presents on its left, or that on its right. As we built up in the previous lesson, we said that in our binary tree and in our binary search tree implementation, we were going to have each node store both a key and data, along with pointers to the node to its left, as well as that to its right, and then one back to the parent node. We said that if a child or the parent node was missing, the respective pointer would point to the null pointer. The nodes are going to be arranged in the binary search tree to satisfy the binary search tree property. If X is a node in a BST, binary search tree, if Y is a node in the left subtree of X, then Y's key is going to be less than X's key. If Y is a node in the right subtree of X, we'll go ahead and by this property, Y's key is going to be greater than or equal to that of X's. So here were a couple of examples of binary search trees that I showed in the previous lesson. What I'm going to go ahead and say that for the current lesson today, we're going to assume that the data and the key is kind of the same. The reason being is that I'm not going to worry about the key values as we're implementing our iterators. Instead, I'm only concerned about the data stored within a particular node, because that is what we're going to get back upon dereferencing a particular iterator, which means that you can go ahead and just, for our purposes, assume whatever value is being depicted in a particular node in a tree, provided I give an example, which I will. Go ahead and just assume that's the data residing there, not the key value. I know this is a bit of a divergence from what we saw before, but I'm going to use these diagrams to hopefully illustrate what's happening as we're constructing our binary search tree iterator, as well as what's going on as we're moving, say, from one node to the next with that next operation. But I'll do my best to make that clear as we're going through this, but I will remind you of the structure of the binary search tree that we implemented in a previous lesson, as well as the nodes comprising it. So starting out with the nodes here, we said that it was going to be a class template. It was going to contain objects of this type would contain 5 data members, a parent, which is just a pointer to another node of the types used to instantiate from this class template. Same with left, same with right. Data was going to be of type T1, and then a key. We provided a second template parameter for this class template so that the key could theoretically be a different type than the underlying data, which I think is a sensible design decision here. So as we continue through, we introduced our binary search tree. It was templated as well. So we had a class template with 2 type parameters, T1 and T2. And again, the first being that storing, communicating the type of the data, and then the second communicating the type of the tree. And you can go ahead and look through this just as a recap, pause the video as necessary, but we're not going to be working with this too much today. What we're going to be working with is going to be the iterator type that we're going to construct together. I did forget, looking at the schedule, the updates that will be necessary to go ahead and include or absorb the iterator into this class, so that begin and end functionality. I'll do my best to remember to tag that on ad hoc at the end. So just to remind you what an iterator is, or more or less the operations that we're looking to implement with our iterators, because that is the topic of today's discussion. The key operations of an iterator are going to be to access the element we're currently visiting. This will be through the dereference operator. Move to the next element in the sequence, which will be the pre-increment operator. I'm not going, just for today's lesson, I'm just going to focus on the pre-increment implementation because it'll make things a bit easier. And kind of the process of implementing an iterator for a nonlinear structure is a bit more involved and thus time consuming than what it was for linear structures with the doubly linked list, as it would have been for, say, a vector. Anyhow, hang tight, we'll get there. So we'll additionally implement today an ability to check whether two iterators are visiting the same element, and we will go ahead and implement both equality and inequality. Remember from the last lesson, I mentioned that there are kind of many different flavors of iterators out there in the wild. Most, if not all, support the key operations that we've just noted here, though there are iterators that support additional operations, and some of the STL algorithms may require an iterator of a specific kind to be used within that algorithm. So anyhow, we'll go ahead and get started. We're going to introduce our binary search tree iterator as a forward iterator to keep things simple. So it's only going to focus on these key operations that we introduced, reintroduced today, introduced more sufficiently and in detail in the previous lesson. So let's go ahead and get started with our implementation of a binary search tree iterator as we'll define it. I'll go ahead and begin with kind of an overview of the classes, and then I'll actually get into, well, the class and then the actual data members, some rationale for them, which will be reinforced as we're going through the constructor, the pre-increment operator, as well as the rest of the operations. So let's go ahead and get started on that.